Hello and welcome to my video on compression and work done from compression on an ideal gas. An ideal gas. Remember, this is the ideal gas equation right here. So, let's start with our classical idea of work. Work equals F dot dr. And these two are vectors. So this dot product gives out a scalar. So work is a scalar. It's just going to be a number. And that number is just a regular scalar, and we can measure it. And so we can also rewrite this as F sub x dot delta x. So this is going to be the force in the x direction dotted with the change in x. Now this is for just one dimension here, but it's a simple version that we will use today. The equation you might also know is just force times distance. This is just regular multiplication, but it'd still be F sub x basically, or F sub whatever distance vector this is. So this is probably what you remember, work equals force times distance, but we're going to work with this, force in the x direction dot delta x. That's what we're going to be working with today. Okay, and so if you remember also from our last video, force equals pressure times area applied to it. So this is good because now we have a force to plug into this. So let's rewrite this. Work equals pressure times area times delta x. Now this part right here is pretty interesting. The area times the delta x. What does that really mean? Well, let's draw a little box. We have an area here that the pressure is being applied to, and the gas is inside this box. Oh, that's a bad box, I'm sorry. But it's inside this box. And let's say this side right here is the area we're working with. Well, what we're saying is the delta x is actually this side right here. And let's just say it's compression, so it's delta x moving this way. So it's lowering the volume of the box. But what that really is this area times the change in this length. And you know what that is? Well, this is actually the change in volume. So that's really good for us to look at. So work equals pressure times change in volume. Now this is a really good equation to know, especially just for regular basic physics. But let's take it like one step farther and instead write it in terms of, oh, I'm also sorry, this is negative pressure times volume because we're lowering the volume, so it's going to be a negative work done to it. So again, let's take this one step farther and say work equals, when you see a delta x, what we can do is just integrate. Integrate from V initial to V final of negative P of V dV. So this delta V turns to a dV, and we write pressure as a function of volume. And so where do we get pressure as a function of volume? Well, from the ideal gas law. We have it written up here, but let's write it right here. Pressure as a function of volume equals N K T divided by V. This is pressure as a function of volume. So let's plug this into our integral. And we get work equals the integral from minus V initial to V final. Negative N K T over V dv. And let's solve this integral now. It's going to be negative n k t integrate 1 over v dv. And this is just a basic natural log function. That's what this integral is. 1 over v is the integral of 1 over v is the natural log of v. So minus n k t natural log of v. And I'm running out of room here, but I would write these limits as well. Let's just go for it. Work equals minus n k t natural log of v final minus natural log of v initial. Now using log properties, we can just combine these two logs, can't we? So minus n k t natural log of v initial over v final. And now we can even take it one more step farther with our log properties. Pull this negative over here, and this just puts in the reciprocal of the natural log. So our final equation is going to look like work equals n k t natural log of v final over v initial. And so this is really cool. So now we know, if we know the change in volume, or at least the initial and final volume, and the temperature, we can find the work done to this system. And let's talk about why this temperature is here too. We didn't integrate with respect to temperature because we're assuming it's constant through this whole process. So basically what's happening is this box is being compressed so slowly that the temperature is not changing. So temperature has to be constant for this system. It's called an isothermal system. And that's why this is an isothermal compression right now. And so what we can do is use the first law of thermodynamics. Q equals delta U minus W. So the total energy of change in energy of a system is the work plus the heat. I just rearranged it a little bit here. But now what we're going to say is that the work done, or delta U done, is going to be 0. There's no energy change because the temperature is going to be constant. So what we have to assume then, if temperature equals constant, delta U equals 0. There's going to be no change in energy in this system. So the work done has to equal the heat of the system, the heat flowing in the system. And that's really good to know, because now we can say that the heat flowing in or out of the system is equal to nkt natural log of v final over v initial. And that's really useful. Now we know the heat flowing of an isothermal compression or expansion. Now one last thing I want to show you is a drawing of the PV diagram on this system. So PV as in pressure as a function of volume. And that comes from this 1 over V here, and it goes in the shape of a hyperbolic function like that. And so what this says now is if we know an initial V and an ending V, we can actually find the heat going through the system on this curve right here. And that's really useful. One other thing to note is that if you have multiple systems, the PV functions are all hyperbolic like that. So you can find this volume and this one and go through here. And since they're all hyperbolic, they actually don't cross each other either. Alright, and so that does it for this video. Thank you for watching.